The topic of today's video is the Kohn Sham scheme. So in this video, I'm going to explain everything that is related to this Kohn Sham scheme. So moving on towards the introduction. So the current TFT is based on the previous works of Kohn and Sham. So who were Kohn and Sham? Kohn and Sham were two scientists, and their work serves as a basis of current form of DFT. And what is DFT? You already know that DFT is density functional theory. So the Kohn-Sham theory is based on the following statement. The ground state electron density of an interacting system will also be the ground state electron density of a non-interacting system with an effective potential V effective. Okay, so first of all, you need to know what is a non-interacting system. So let's just say that we have a many body system. We have a multi-electronic system in which there are a bunch of nuclei, in which there are a bunch of electrons, and in a non-interacting system, when we consider a non-interacting system, we just neglect all of the interactions between the nuclei, between the electrons, between all the particles. Okay, we just have to neglect all type of interactions between these particles, whereas an interacting system is that system in which there are interaction between the electrons, between the nuclei, between electron and nuclei, and these interactions include the electronic repulsion, the electronic nuclei attraction, the nuclei repulsions. Okay, so these are the interactions that are present between the particles. So in an interacting system we consider these interactions, whereas in a non-interacting system we do not consider these interactions. Okay, so what did Kohn Sham did? Kohn Sham considered a many-body, a multi-electronic system that is composed of a non-interacting particle. So this is just a fictitious system. Okay, and how did they solve their system? They used a modified form of the Schrödinger wave equation for a non-interacting system that produced the same value of the ground state electron density as that produced by the Schrödinger equation of an interacting system. Okay, so they used the Schrödinger equation to find the electron density, to find the ground state electron density of a non-interacting system, and this ground state electron density came out to be equal to the ground state electron density of an interacting system. So that was our basic statement. Let me just explain it. What did they do? They considered a non-interacting system and then calculate the electron density by using modified Schrödinger wave equation, and you will get a resultant ground state density. Whereas now you have to consider an interacting system and calculate the electron density by using the simple Schrödinger wave equation, and you will get a resultant ground state density. So according to the Kohn Sham, the non-interacting system, the ground state density of a non-interacting system obtained by using modified Schrödinger wave equation was equal to the ground state electron density of an interacting system obtained by using the simple Schrödinger wave equation. So this was the basic statement of the Kohn Sham theory. So moving on towards how did they modify the Schrödinger wave equation? What did they do so that the ground state density of a non-interacting system became equal to the ground state density of an interacting system? So they used a modified form of the Hamiltonian operator, and this Hamiltonian operator is given by H is equal to V effective minus 1 by 2 del squared. So this V effective is the effective potential, and this was the modified form of the Hamiltonian. And now if we move on towards the energy functional, the Kohn Sham energy functional, it is composed up of two parts. Okay, and these two parts are the known component and the unknown component. Okay, so now the energy functional is given by E psi is equal to known energy. This is the known component of the energy functional, and this is the exchange correlation of the energy functional. This is the exchange correlation part of the energy functional, and this here is unknown. Okay, so this known part can be calculated easily, whereas we cannot calculate this exchange correlation part. Okay, so if we cannot calculate the exchange correlation part, then how do we solve this equation? Well, the exchange correlation part, the exchange correlation part can be evaluated by using different approximation method. For example, GGA, that is the generalized gradient approximation, and then we have the LDA, etc. So these are some types of the approximation that we have to introduce in order to solve the exchange correlation part. Actually, what really is the exchange correlation part? Well, it involves all the errors that are associated with a non-interacting system. Because as you already know that what we are considering a non-interacting system, and when we have neglected all type of interaction between the particles, then there should be some error. Well, this exchange correlation part take cares of all that error, of all these errors. Okay, this term contains the non-classical electrostatic interaction energy and the difference between the kinetic energies of interacting and non-interacting system. So this term actually take cares of all the errors that are associated with non-interacting system, just I have told you before. So if we move on towards the total energy, you know that the total energy of a system can be represented by the sum of kinetic energy and the potential energy. So, if I talk about the kinetic energy can be taken into two parts. And what are these two parts? These two parts are TSN and TCN. Okay, so this first part, TSN, is the kinetic energy of non-interacting particles. And this second part represents the kinetic energy of interacting system. And so it is also known as the correlation term. And as you know that the correlation terms are calculated by using the approximation method. So this part, TCN, is calculated by using the approximation methods. And again, this first part, that is the kinetic energy of the non-interacting particles, can be represented by Ts phi I n is equal to minus 1 by 2 summation I to n integration dr phi I hysteric r del squared phi I r. This is actually an equation through which we can calculate the value of Tsn. Again, let me mention it here that TSN can be calculated, whereas TCN, the correlation term, cannot be calculated, so we use the approximation methods like GGA or LDA, etc. Here, I can say that phi I are the orbitals of non-interacting electron system. Okay, so it's just a hard term to grasp. You can just say that this phi I is the one electron wave function, because as you know that we are talking about a non-interacting particles, so this phi I here represents the one electron wave function. Okay, so now moving on. Okay, so again, the electron-electron interaction energy can also be taken into simple and complicated parts. So when I talk about the electron-electron energy, we have VHN, VXN and VCN. So VHN is called the Hartree term, and this Hartree term can be calculated through this equation: half double integration dr prime nr prime r minus r prime. And the other parts, the Vxn here represents the exchange energy, and Vcn here represents the correlation term. And as you know again that the exchange and correlation terms are calculated through the approximation method, whereas this VHN can be calculated by using this equation. Okay, so now the Kohn Sham energy functional can be given as, so when I talk about the overall Kohn Sham energy functional, then it is the sum of the kinetic energy and the potential energy. So the kinetic energy, as I have told you before, is composed up of Tsn and Tcn, whereas for the potential energy I can write Vhn the Hartree term, Vxn the exchange term, Vcn the correlation term, and again Enn, that is the repulsion between the nuclei. Okay, as I've just told you before, this Tsn term can be written as Ts phi I n, and again I can write Exc in place of Vxn, Vcn and Tcn, because as you know this correlation term and again this exchange term and this Cn term are actually the exchange correlation terms. So I can write all of these three terms collectively as EXC. Okay, so EXC must be equal to TCN, VXN and VCN. So TCN, VXN and VCN, I have taken all of these three terms to be equal to EXC, that is the exchange correlation energy. And this VHN I have written just like that, and this ENN I have just written like that. Because as you know that this and this term can be calculated, whereas this term has to be calculated through approximation methods. Okay, so now the final form of the Kohn Sham equation can be written just like this, because as you know the Schrodinger wave equation is H psi is equal to E psi, and here what we have done, we have just used the modified form of the Hamiltonian operator, and this modified form of Hamiltonian operator being applied on an electron density nr, and phi I r is equal to EI phi I r. So that is the final form of the Kohn Sham equation. Okay, so now there are some few points that you need to understand. The non-interacting wave function of a many-body system. Okay, so what we are talking about is the non-interacting wave function, means the wave function of particles that are not interacting with each other, is a Slater determinant of one electron wave function. Okay, so the one electron wave function are also known as the Kohn Sham orbitals, and the non-interacting wave function is actually the Slater determinant of the one electron wave functions. And the non-interacting charge density can be obtained by this equation. Nr is equal to summation I n phi I r square. So the total charge density is actually the summation of one electron wave functions. Again, first we have talked about the non-interacting wave function, and then now we are going to talk about the interacting wave functions. Okay, so the interacting wave function of a many-body system is a superposition of many Slater determinants. Okay, and the interacting charge density is now defined as Nr is equal to summation I to n alpha I phi I r square, and this alpha is actually the term that is representing the interaction between the particles. So the interacting charge density can be represented by this equation. Okay, so now we have the self-consistency in Kohn Sham scheme. And this is the most important step in the Kohn Sham scheme. First of all, what you have to do, you have to guess an electron density. You have to make an initial guess about the electron density. And using this electron density, you have to calculate the effective potential. Okay, you have to calculate the effective potential using this equation, and then you have to solve the Kohn Sham equation, and this is the equation that I have just told you before. This equation, this is the Kohn Sham equation. You have to use this Kohn Sham equation, so you have to solve this Kohn Sham equation. So after solving this Kohn Sham equation, you have to calculate the electron density again. Okay, you have to calculate the electron density again. So if the electron density comes out to be equal, then we can say that there is the self-consistency in Kohn Sham scheme. And by same I mean the final density that has come out after calculation is the same as we have guessed. Then we can say that this is the self-consistency in the Kohn Sham scheme. And if the answer to this equation does not come equal to our initial guess, what we have to do, we just have to change the initial guess, and then we have to again calculate the effective potential and solve Kohn Sham equation, then calculate the density until we get the same final result as we have guessed the initial result. So when our answer does not become equal to our initial guess, we just have to change our guess and then calculate all of this to get an answer. So we have to do this again and again and again until our final answer become equal to our initial guess. So in that case, there will be a self-consistency in Kohn Sham scheme. So the final density that has the value equal to our initial guess is the true ground state electron density, and this electron density can be used to calculate all the ground state properties of a system. So that was all about Kohn Sham theorems and self-consistency in Kohn Sham scheme. So if you have any question, you can ask me in the comments. And a subscribe would really matter. Thank you and Allah Hafiz.